Hi, welcome back. In this video, we will write an algorithm which gets a sentence, which usually is a question, for example, what are vegetables? And then the algorithm also has access to a variable which has text, and in that text there are several sentences. So the algorithm should find the answer to that question in that input text. So this is a common case for chatbots when you have a chatbot which answers questions. In the next videos, we will build a chatbot which answers Wikipedia questions about a certain topic, and the chatbot will read a Wikipedia article and give you the answer. So that chatbot is based on this algorithm that we will write in this video. So in this algorithm will get this question, and then it will return the sentence among these sentences, the sentence that is the most similar to this question. So what are vegetables? We expect to get vegetables are all plants from this algorithm. For this, we will use NLTK, the library we have been using. So we will reuse some of the code of that NLTK library, the code that we wrote previously, and then we will use scikit-learn, which is a library that allows us to do this matching of the best sentence given another sentence. So let's first see what code we need from the NLTK library. We actually need this lemma function in here, which, just to remind you, what this does is it gets one sentence as input and it tokenizes that sentence into words. So it generates a list of words. Each word is an item of that list. So one list here, and then for each item we find out the tags, which is the type of the word. So for each word we know what type of word that is a verb or a noun or etc. And then we convert each word into a lemma. So we find the lemma for each word. And if we get that function, for example, if we input this sentence into that function, we would get as output from that function a list which would look something like what be the lemma of R and vegetable, the lemma of vegetables. So that is the output of that function, this kind of list. So we need to get that and copy it in here. So we do have that function now. Then what else do we need? A scikit-learn dot feature extraction dot text import capital T F IDF vectorizer. That is a class which will do a statistical analysis which will find out the importance of a word in a corpus. A corpus is basically a piece of text. So this will help us build a matrix where we have the importance of each word, and that will help us to compare the similarity between sentences afterwards. You'll see how that works. So execute that. And then we need to create an instance of that class. Now, I said that this class is working on finding the importance of words. So therefore, this needs to have some sort of list as input, a list of words. But instead of inputting the list of words here, this class is designed to get as input a tokenizer. A tokenizer which tokenizes sentences, so it converts them into words, and we do have that function. So that is the lemma function. So this function should get a sentence and should return a list object type made of words. That is what we do there. Execute that. If you see TV, there's nothing to see right now because this is just a representation of the class without any values yet. Now we need to do that finding of the word importance using another variable here, tf for this, and we need to use that object type and point to the fit transform method, which is an algorithm that will get the sentence tokens as input. Now, what is the sentence tokens? Well, this is a variable that we haven't defined yet, actually. So we need to define this, perhaps under the function here, in a new cell. So we need to calculate the sentence tokens. This will be nltk.sendTokenize, and we get text as input. So we're working on this text in here, and if you see what we get from this, is a list of 3 items. Each item represents or is a sentence of that text. So originally vegetables were collected from the wild by hunter-gatherers. That is the first sentence. And then we have vegetables are all plants in here, and so on. We have 3 items in that list. If you got an error saying that you need to download some NLTK dataset, then just execute that code that is shown in the error to download that dataset. Then I can execute that. Since I have this variable now defined in here, I can go ahead and execute it. Now this asked me to download that, so I'm going to create a code cell in here, download it, and then execute again. We've got an error here, the lemmatizer is not defined. So it's talking about this line. That is the lemmatizer instance. This one in here. So I'm going to get that code and just place it in here. Execute. So that's the lemmami function, that's the lemmatizer. Now we go down and execute that again. We need the WordNet library as well, so I'm going to convert that in here. So I'll execute that in here as well, execute that again. If you want to see what TF is, you can just call it. So it's a matrix 3 by 8. Now, I know you are completely lost at this point, so I want to show you what this looks like actually. So this is an optional step, this code cell here. To see this matrix, you can do tf.toArray. That is a method that will display the actual matrix. This looks intimidating, but I'll explain you what it means now. So this is a matrix made of lists. We have one list here, so it starts in here and it ends in here. That is the first list. Then we have the second list, it starts in here, it ends in here, and then we have the third list. So we have one list for each sentence, because you see that this TF was built from the sentence tokens variable, which is this one in here. So it's a list of 3 items. Now, let me copy that list and just put it in here temporarily just to see what's happening here. So one sentence, one list. And then if you look inside each list, you'll see that we have 1, 2, 3, 4, 5, 6, 7, 8 items. 8 numbers. The second list also has 8 numbers if you count, and the third one as well. So each of the lists have 8 items. Why 8? Well, that is because the longest sentence in our text has 8 words. We can count 1, 2, 3, 4, 5. This is not counted, these articles. So 6, 7, 8 words. And each number represents the weight of each word in the entire text. So, for example, 0.3 means the weight of originally in the text is that number. And then we have vegetables, 0.52. It has a bigger weight because it's being used here as well and here. To get a better representation of this matrix, you could use pandas, import pandas, and then create a data frame from pandas.dataframe. So again, this cell here and that one are optional. They are just to show you what's going on in here. And then you say tfeed.toArray as a source of the data frame. The columns will be TV, so the vectorizer, which we defined in here, dot get feature names method. So call that method and then print out df in here. So that is a better representation. You see the weight of the word B is 0.3 and the weight of collect is 0.52 in the first sentence, and then the weight of those words in the second sentence, and so on. For example, the weight of originally in the first sentence is 0.52, but the weight of that word in the second and third sentences is 0 because there's no such words in those sentences. That is why we have all these zeros in here and also here, so it's the same matrix. Alright, so this is how it works, but we need now to add another sentence to the sentence tokens. So when we created the sentence tokens, we use the text variable. We need to also append the question variable in that list of sentences. The question variable is this one, which has this question. So execute that. Now you see that sentence tokens is this list, and then you execute all the other cells to redefine them with that question added, all of them. You see the array now has 4 lists instead of just 3, and we delete that. And we also see the data frame has 1 more row at the end. And now to find the similarity, finally, let's say values are equal to cosine similarity, which we need to import from sklearn.metrics.pairwise import cosine similarity. So cosine similarity now finds the similarity between two matrices. The first one being TF minus 1. So TF, you know TF is this. And TF minus 1 is the last item of that matrix. So the list that represents the question. So we want to compare that question to the entire matrix. TF minus 1 with TF. Execute that, and this is what we get. We get an array, and this array now has 4 values, as you see. Each value represents the similarity between the question and each of the sentences in the text. So that means how similar is our question, what are vegetables, with the first sentence. So the first sentence is, let me get this just to keep it here for explaining you what's going on. So what are vegetables is similar with the first sentence at this coefficient, 0.39. And then it's similar to the second sentence, which is vegetables are plants. It's 0.59, the similarity coefficient for that, 0.46 for the other one. And then we have this 1. 1 is the similarity between the question, what are vegetables, and the same question, what are vegetables, because you know we appended that question to the sentence tokens. So the similarity between two identical sentences is 1. It's 100%. Now we want to find out which sentence is the one that has the maximum value in this list. So let's find that out. We need to extract the index of that sentence. We do that using values.arg sort. You call that method, and if you see what index is, now you'll get an array, but you only want the first list because we have nested lists here. So we get the first list, we execute again. You see now there's no two lists, but it's only one inside. And then out of that first list, we get the -2 index. So that will give us the index of the maximum value. Actually, it's not the highest value, it's the second greatest value, because the first one is 1. So if we applied -1 here to get the last value out of that sorted values, we get an index of 3. So that's the index for that, but with -2 we get 1. So index 0, index 1, we get the correct index for that maximum value. So that's a variable we need now in just a bit. However, first we want to point to values flat. So we want to say values.flatten, and we get this. So it's the same values basically, but we don't have these two nested lists, we have only one list in here. Lastly, now we can extract the coefficient, which is equal to the values flat matrix -2. So we want to get always the before last item. So now we have the coefficient, and we could say something like, finally, if coefficient is greater than, well, let's put a threshold of 0.3, then we return, or we print out whatever we want to do. We print out from sentence tokens, we print out the item with index 1. If you execute that, you get the answer of that question. So the question was, what are vegetables? And the answer is, vegetables are all plants. So that is how you can get the most similar answer given a question from a piece of text using this quite advanced algorithm that you saw in here. So thank you for following this, and I'll talk to you in the next videos. See you.